Okay, so welcome you all to this first colloquium for the students of our department. It's really a great pleasure and honor to introduce the speaker of today, Emmanuel Trélat from Sorbonne University. Let me just okay. Let me just mention some of the works of Emmanuel. He got his Felix Klein Prize in 2012, the Blaise Pascal Prize in 2014, and more recently in 2018 he was invited speaker at ICM. He's a great expert of optimal control and Subramanian geometry, and we are very pleased to have his talk about everything is under control. Please.
Thank you very much, Fabio, for your very kind words. And well, I'm very glad to be there and to have the opportunity to speak and to make some advertisement to control theory. Control theory under the viewpoint of mathematics. So maybe, since maybe not all of you know what is control theory, I would like to introduce my talk just by mentioning several applications of control. Because usually, you know, when you speak with someone, you tell him, okay, I'm a mathematician. Well, okay, but what do you do? And you say, I do some control. So the first thing that people imagine is that you are, you know, in a train and controlling people. No, but this is not at all this. No, control theory is rather, let me try to define it in few words. Let us say that you consider a system, and I'm going to give you a number of examples of systems, of concrete systems, on which you can act. You can act on a system by means of a control, a command. So this is a control system. For instance, a system that I will like to consider during my talk is you consider a car. So you are driving a car. Everybody does that daily, maybe. Okay. A car is a control system on which you can act by means of turning the steering wheel, because acting on the steering wheel, you act on the wheels of the car, and maybe you can try to control it. So controlling a system is given, let's say, by some differential equations, which do depend on parameters. And parameters evolve according to your choice, and they evolve with respect to time. For instance, when you drive your car, at every instant of time, you are turning the wheel either left or right, and thus controlling the trajectory of your system. And maybe also you are accelerating and braking. And so the car is a very good example of a control system. There are many examples in mechanics. I just mentioned a car, but what we can also drive is the motion of a rocket, of a satellite, of a robot. Of course, you can try to drive robots to make, for instance, some remote surgeries or something like that. So in mechanics, there are plenty of examples that you can easily imagine. But this is not the only topic in which control theory and so mathematics has a strong intersection. Think also about electricity and electronical device. For instance, okay, this smartphone is full of control theory. As soon as you send an SMS or a photo, an image to a friend, you are doing actually some control theory, because you are also controlling a system, which is maybe the photo that you send some signal, and the smartphone of your friend will have to reconstruct a signal. So the reconstruction of this signal may be thought of as a system for which you have an initial point and a final point that you want to steer the system to. This is also an example. In chemistry, let me give maybe my favorite example in chemistry. I do not want to compete with you, Italian guys, but imagine that you are cooking some pasta, okay? Well, you are doing some control theory because in chemistry, they look at reactors. So in our case, the reactor is a recipient in which you put some water and then you get hot water and you put pasta inside. So what is your control there? The control is the temperature of the water, and you act on the temperature, so you do some control, depending on time, right? Right. And so you choose the control in function of time in order to steer your system, which is the pasta. The pasta has an initial state, which is, let's say, rigid, okay? And at the end, after some time, 12 minutes maybe, or 10 minutes? Fine? 9. I forgot that I am in Italy, sorry. I said I do not want to compete. But after a certain horizon of time, capital T, that you choose also, you want the pasta to be steered to some final state, which may be al dente, for instance. Okay, so this is a control system with a very simple control, of course, in that case. But you can imagine that in general, in chemistry, when you are making some distillation, for instance, the processes inside can be very complicated, very much nonlinear. Think about kinetic equations in chemistry, for instance, where on a given equation, on a given chemical reaction, you act by choosing the temperature. And the temperature enters the kinetic equation in a very, very nonlinear way, thanks to Arrhenius' law or something like that. Okay, many other examples. Think of applications of control theory, for instance, in biology, in medicine. For instance, there is a topic that is very, very much under study currently, which is you consider a system of cells. You have, let's say, healthy cells on the one part, and on the other part, tumor cells, because you would like to cure a cancer, typically. So these two populations of cells are interacting together, and you would like to control this population. Of course, what you would like to do is to eradicate, to kill the tumor cells. So typically, your control there is the chemotherapy. You put some drugs. The quantity of drugs that you give in function of time is a control that you choose. And you would like to choose the control adequately so that after a certain horizon of time, you have only a minimal number of tumor cells, say. In that case, we speak of optimal control because not only we want to control a system, but we want also to minimize some criterion after some horizon of time. This is an example. Another domain in which control theory is also pretty much used is economics. Imagine that you have a model of a market evolution. You are playing on a market by buying some things and maybe selling some things. And at the end, after a certain horizon of time, capital T, you would like to maximize money, typically. So this is also optimal control. And in that case, we do not want to minimize something, but maybe to maximize the quantity of money that you get after some time, capital T. So all of that are examples of topics in various disciplines, as you can see, in which mathematicians can interact with many colleagues. This is why I do like, personally, control theory, because it is a domain in which you can interact with many, many people in many different disciplines. So the main issues that I will try to illustrate in my talk that are usually investigated by the mathematicians are the following questions. I will focus only on the three first. The first question, when you have a control system, is the question, of course, of controllability. You have a given system. Think of your car. You are given an initial point and a final point. And you would like to know, okay, am I able to steer my control system from this initial point to this final point? It's not clear. It depends. Okay, this is the question of controllability. It's a question of existence for a mathematician. Once this first question has been answered, in general, we are doing, or we can do some optimal control. So once you know that you can steer the system to some final target, maybe you would like to do it, moreover, by minimizing or maybe maximizing some criterion. For instance, you would like to go there in minimal time, or maybe in minimizing the consumption, or something like that. And once you have done some optimal control, in general, another also natural question is the question of stabilization. Once you have determined a kind of perfect, a kind of nominal trajectory, of course, you would like to make it robust with respect to possible perturbations. This is the stabilization that I will also investigate and illustrate in my talk. So let me start with the question of controllability. You are given a system. Here, I illustrate this talk with photos from aerospace because, well, my personal taste in mathematics has led me to study problems of aerospace. And this is why I will very often take examples coming from aerospace. So for instance, in aerospace, you have a given system, which can be a rocket, a satellite, something like that. This is your mechanical system under consideration. And maybe you would like to steer this system from a given initial point or initial configuration. For instance, if you have a satellite, maybe at the beginning the satellite is on a given orbit around the Earth, and you would like to act on this satellite and steer it after some time to another orbit. This is the orbit transfer problem. First question, is it possible? How to solve this question of controllability? So let me illustrate it. And let me illustrate it by considering the first following problem. Let us say this is a car. Okay, you need imagination to make mathematics, of course. So imagine that this is a car. Okay, and what you would like, maybe I would need a third car. Do I have a third car? Maybe this is a first car. Okay, this is maybe a truck. Okay. And you are on the road. Okay, my problem is the following one. I am driving my car, and I would like to get to some parking. So I would like to make some parallel parking, right? So here, along the street, I see that there is some room. What can I do? What would you do with your car? Imagine that you do not know anything about constraints that are in the car. What would be the very natural motion? I come here, and I would do like that, right? Let us see. It would be, in some sense, the perfect parallel parking that I can illustrate as follows. Up. Okay, but you know that it does not work like that. It does not work like that because on your car, you really know that, well, the wheels that are at the back of the car cannot move, okay? But only the wheels that are at the front of the car can move to the left or to the right. So this is a serious constraint on your car. And you know that in order to make some parallel parking with a car, you all learned about that while learning how to drive, you have to make a motion which is not at all natural. You have to do something like that. Okay, this is the kind of motion that we all learn when we learn how to drive. Okay? So you cannot move your car, let's say, in an orthogonal way. It's impossible. Okay, so this is already control theory. And by the way, this problem, when you model it in terms of differential equation, because here, let us say that you have the familiar form of a control system in mathematics. This is a kind of ODE, ordinary differential equation, you see, where x, let us say, is the state at the time t. But moreover, this differential equation also depends on a parameter that you call the control. And the control is itself depending on time. Think you are driving the car. At every instant of time, you are choosing a parameter, which is the control, in order to bend, in some sense, the trajectories of your control system and try to make it, try to make an output which is the desired output. Well, and if you model the parallel parking in terms of mathematics, you immediately obtain a problem that is not so obvious. That is already not obvious at all. Okay. But now what happens, what happens when moreover to your car, you attach a trailer, like a caravan, for instance. And now you would like maybe to make a parallel parking with a trailer. Do you know how to do? Huh? It's not easy. It's not easy because when you go back with your car, you know that if you turn too much to the right, then the caravan will go to the left or something like that. It's rather counterintuitive. So personally, you know what I do with my own trailer? I have a trailer. This is not my dog. I have a trailer, and when I want to go back with my trailer, I simply untie the trailer, okay? I detach it from the car, okay? I go by hand, and then I get back with my car. It is simpler for me. So my colleagues are always laughing at me because they tell me, oh, okay, you the control expert, you are not even able to implement what you teach. Okay, well, okay, it's like that. Now, since we are mathematicians, you take a car and you attach to it n trailers, and it becomes much less obvious. It leads actually to mathematical problems that are nowadays not even solved. Okay? So you cannot find many videos on the internet, but at least I will show you how to make a parallel parking with two trailers. So it's not a video, it's a simulation. It's a Scilab simulation, actually. But already it becomes very counterintuitive. So you have your car. Again, a car is a kind of rectangle with wheels, and only the front wheels can move left or right. This is the assumption. And you attach to your car two trailers. Okay, and what you would, this is your initial point, and this is the final point. Question, controllability problem, how to steer the system from this position to that final position. It's not obvious. Let me show you. The motion is rather counterintuitive, and actually this kind of motion can only be computed thanks to mathematics. And you have application of that. When you have big tracks that transport very big materials, like in Toulouse in France, where they often transport some parts of big planes. So you may have 2 or 3 trailers. And of course, the constraint is that the track, when it moves, has to make very specific and complicated motion while avoiding some obstacles. Of course, the planes do not have to be in collision with houses that are near the route. Okay? So in that case, in order to be a pilot of such a big track, you really need computers. You need the help of quite complicated calculations done with mathematics. You really need that. And now, to still illustrate the question of controllability, I would like to settle another problem. And I realized that I forgot to bring an apple. Does someone has an apple or something, or maybe a ball or something like that? Ah, you have, fantastic. I will give it to you back. Thank you. Ah, so it's. Oh, thank you. You're generous. So I will stay here, maybe. Yeah, it's okay. So imagine, rather, this is an apple. So, okay, but that's fine. And this ball is a convex body. My problem is that I will make roll this convex body on, let's say, on the plane here. Okay, so here is the ball, and I am not allowed to move the ball like that, right? I can only make it move just like that. I mean, I can make it roll without slipping. Okay, this is not allowed, right? Now let me pose a controllability problem with it, which is everything but obvious. Everything but obvious. This is an initial position, right? Now let me prescribe a final state there. What is a possible trajectory to steer this control system from that initial point to that final position? How would you do? So maybe the first intuition would be, okay, let me start along a straight line, right? But if you start along a straight line, probably you will come to the final point, but not with the good orientation. Okay, because it is an object which has an orientation. Let us imagine the end of the apple, for instance. The end of the apple here should be vertical, and at the end point it should be also vertical. So I cannot use probably the straight line. Unless I am very lucky, the straight line is not a solution. So probably you will have to move like that, to make curves, right? Let us, thank you. Are you an expert of control theory? Thank you. Let me show you a software which is done with MATLAB that implements exactly what I said. Okay, so let us take a body which is, let's say, a saucer, or do you prefer a saucer or rugby? Maybe rugby, why not? Okay. We want to make some rolling, so let me give an initial position, a final position, and let me also prescribe an initial configuration and a final configuration, like that, right? So now here is the problem. I have given to my convex body an initial configuration, a final configuration, and I would like that the software be able to compute a trajectory along which, when the body will move without slipping, along which the body will reach its final configuration with a good orientation. So what the body will do is start from a given trajectory, which is in red, which is an arc of a circle for some mathematical reasons. You start with that, and what the computer will do is to deform the circle in order to make it admissible. That is, in order that once the computation will be finished, when we make roll the body without slipping, it will come to its final point with the good configuration. Let me show you the calculation. So here you will see the trace of the curve on the convex body. It's already done because my computer is quick. So what the computer did is deform the trajectory in order to make it admissible. And now we can visualize the result. We make it roll up, and it comes to the good final configuration. Okay. So what this video illustrates two things. The first thing is that I am allowed to say it. Actually, in our offices, we play very much. Okay? We have fun. This is the first thing in mathematics. If you are going towards research, you have to take pleasure in it. And believe me, we have much fun, actually. The second thing is that even though we have fun, okay, this is a funny software, but actually it illustrates many things, and it can be adapted to very concrete and difficult industrial problems, right? So actually by playing, we also try to contribute to make some advances, and for instance, industrial advances. Okay, so this illustrates, you see, I do not speak much of mathematics, but rather advertising them. This was illustrating the controllability part. Now, as a second part, let me illustrate the optimal control part. I mean, once you have solved a controllability problem, you have an initial point, you have maybe a final point, you know that there do exist some trajectories steering your control system from the initial point to the final point. And in general, when there exists at least one, in general, there exists an infinite number of possibilities most of the time. For instance, when you want to do a parallel parking, well, you know that there exists an infinite number of ways to do parallel parking because you may be wrong, because blah, blah, blah. But probably among all these possibilities, there is one which is better for a given criterion that you are given. For instance, you would like to minimize time, or to minimize consumption, or to minimize or maximize something else. What happens, for instance, when you make some parallel parking by minimizing time? Do you think it's reasonable? Let us see. Maybe not so much. Okay. These are minimal time parallel parking procedures. Let me show you. I'm not driving the car. Another minimal time strategy, which is not so good for the... this one is also funny because it's for parity. You know, she's a woman. And maybe a last one, and after that, we come back to the talk. Okay. Right, but as you can see, it depends on what you are doing, but in order to make some parallel parking, probably trying to minimize time is not a very reasonable criterion. What you would do rather, because oil is costing so much, you would minimize your consumption, most probably. And you already feel here that if instead of minimizing time, you minimize consumption, then the optimal trajectory that you will get will not be the same. It will not be the same. So what I say here is something obvious but very important. The optimal trajectory that you will get at the end of the process depends on the criterion that you are choosing in general. Actually, let me tell a bit of history about this problem, because historically, the very first optimal control problem, if we try to date back, actually comes back already to Bernoulli, so several centuries ago. And Bernoulli was asking the very famous brachistochrone problem. In some easy words, this problem says, what is the optimal slide? Oh, let me be a bit more specific. in mathematical terms, here is the problem. You are given a slide. So what is a slide? A slide is given by 2 points, A and B is below, okay? You have a curve, a mathematical curve that is joining A to B, like that, like on these 4 possibilities. Then what you will do is that you will have a small ball, or maybe a child if you want. You put a child there, okay, or a ball, and then you let it be. So the ball is rolling along the slide, and the optimal control problem that you consider here is that you would like to get what is the best possible curve so that the ball will arrive at the point B in minimal time. You would like the ball to be the quickest possible to the point B. What is the best slide? According to you, is the best shape the straight line? One. Yeah, one. Or maybe is the best curve a circle, an arc of a circle, you see? The circle is going tangentially here and tangentially to the end. Who thinks that this slide is the best one? Yeah? Many, yeah? Many. Now you take a kind of very dangerous slide, okay? The slide is almost vertical here and almost horizontal there. So who would vote for this optimal slide? Nobody, yeah. You are reasonable. And here is also a strange one. It's starting also vertically, so it's a kind of dangerous slide. And it goes below the point B before going higher again, like that. Who wants to vote for this slide there? Yeah, also a majority of you, I think. And the majority of you is right, because this is the good answer. This is the optimal slide. But don't worry, for those who voted for the second slide, you make the same mistake as Euler. Euler was thinking that the optimal slide was this one. So, okay, making a mistake like Euler is not very, it's okay, it's admissible. No, the optimal one is indeed this one, and this is the brachistochrone curve. Let me recall the definition of the brachistochrone curve. It's for the mathematicians, it's a cycloid, so it's given by hyperbolic cosine and sine. And if you want to draw it very simply, you take a wheel, so you are going to your bike, and you make some red point on your wheel, and then you advance. Then the apparent trajectory of the red point is exactly a cycloid. Okay? This is one of the possible definitions of the cycloid. These are not arcs of circle. These are hyperbolic cosines and sines. And by the way, if you do some skateboard, this kind of curve is exactly used for skateboards, actually, because these are the curves with which you can go the quickest to the bottom of the skateboard. Okay. And so as I said previously, I'm now going to illustrate optimal control on several examples coming from aerospace. So here is, by the way, the mathematical form of an optimal control problem. This is the kind of garden that we explore when we do some optimal control. And you have a differential equation with a control inside, and we would like to steer the control system from some given initial configuration to some final configuration by minimizing, moreover, some cost functional. Like, for instance, this is probably one of the first concrete problems on which I was working in aerospace. It was the problem of, oops, it works. It's here, okay. It was the problem of the atmospheric reentry of a space shuttle. This was one of the problems I worked on. So you take a space shuttle that is in the space and that is going to enter in the atmosphere. And actually, as soon as it enters in the atmosphere, let's say at around 150 kilometers, you have many frictions with the atmosphere. So what happens for the space shuttle, accelerate. What happens for the space shuttle is that, now, when it enters really the atmosphere, it gets hotter because of friction with the atmosphere. So this is a very difficult optimal control problem in which you would like to minimize the thermal flux. So I mean the effects of warming, the bad effects of warming on the space shuttle. And it happens to be a very difficult problem. By the way, you all have in mind maybe the catastrophe that took place with the space shuttle Columbia. It was in 2003 or 2005, I don't remember. The shuttle was exploding exactly at the phase at which it is very, very dangerous. And well, okay. So this is an example. Another example that took me something like 5 years, something like that, was a collaboration with Ariane Group. Ariane Group, you know, is the new name now for EADS. Maybe you knew EADS, which is this European giant that is launching Ariane launchers. So this group, Ariane Group, is the worldwide leader for launching rockets and so for launching satellites. And the problem on which I worked during 5 years is the problem of trying to design a software that would be automatic and instantaneous. So automatic means without human intervention. Instantaneous means, let's say, less than 1 second or something like that, or 0.1 second. And this software should be able to compute, so very quickly, any optimal trajectory for any Ariane launcher to steer it to some final orbit with a very, very big range. And actually, I can tell you just a bit of this story because this story is a bit funny. It was in 2007 or 8 or something like that. I was giving a talk with some researchers in the room, and in the room there was an engineer of EADS, so of Ariane Group, who is, by the way, Max Cerf, who was then later my PhD student, but who is older than me, actually. And Max Cerf is the guy who is in Ariane Group in charge of computing trajectories for Ariane launchers. Okay? It's daily job. And he came to me and he asked me to send me by email an executable file. Okay, so I said, okay. I received a file that is, you know, .exe. You know, this kind of file that you can execute under Windows, but you cannot open it because if you open it, you do not understand anything. And the guy was asking me, okay, what it is. I said, no, I do not have an idea. I cannot read it. So after discussing with the guy, he was telling me, well, this code that I sent you is actually the code with which we launch the Ariane rockets. I said, what? Well, okay. And I send it to you because I would like to know what is inside. So I'm completely unable to do that. I told him, well, okay, please try to send me the source code. Is the code written? The code was written in Fortran, okay? But the guy told me, well, we lost the Fortran code. So I began to laugh because, again, as I told you, we laugh much. Okay. I told him, well, maybe it's not so serious. Send me the document files because, in general, you have a doc. He said, well, we lost the doc too. So, and I could not believe because since 40 years, actually, EADS and so on, Ariane Group, that is the leader of Ariane in the world, was launching rockets with a code of which they do not have the source file nor documentation. Can you imagine? So, of course, the guy would like to get a new code, actually. And finally, it was his question to me. At the beginning, he told me, well, I would like a software that would be able to be instantaneous. I was kind of naive. I didn't know anything about this problem. So I said yes, stupidly. I said yes. But finally, I needed 5 years to do it because it's not that obvious. But for the industry, it was an incredible gain because with the previous software of which the source was lost, in order to compute only one flight, the software needed between at least several hours of computation and sometimes until 3 weeks of computation. Can you imagine? And this is why, when I was a child and when I could hear at the radio, okay, today the forecast was not so good, so finally we canceled the Ariane launch, and it will be in 3 weeks. And why in 3 weeks? There was this reason. It was because the software was so slow. So now they have, fortunately, a software which is almost instantaneous, which is, of course, a gain for them. And this gain could be done, believe me, because of use of modern mathematics, much mathematics, and mainly mathematics, not so much scientific computing. Okay. I would like also to advertise, because there is much work to be done there, on a challenge that has become so much in a hurry to be solved. It is about space debris. Because, as you probably know, around the Earth, there are many debris. Here you have a kind of picture of debris that are in low orbit, but you have also many debris around the geostationary orbit. And, there are thousands of debris. The biggest of them can even have the size of a bus. They can be very enormous. So, of course, it has become very much dangerous, actually, to be in the space and even to launch new satellites, actually. And the problem has become so much in a hurry to be solved that probably if we do not clean the space in the forthcoming years, probably in a few years we will be unable to launch new satellites. And so it is a bad news because, well, we still have 4G, but what will happen with 5G? We need satellites. So maybe the future is rather in the cable, maybe. Because in the space is so dirty that if we do not act right now, it will soon become impossible to clean. So there is a job that is for sure a job for the future, which is to become a space garbage collector. This for sure. The problem is that it is a very difficult job. Actually, well, it is both an excitement and a disappointment. It is an excitement for mathematicians because it raises a problem that we cannot solve. We are unable to solve it. We don't know. It's too much difficult. So it's an excitement. But also it's a disappointment. It's like that. Okay, and as a third part of my talk, I would now like to illustrate this wording I used at the very beginning, which is stabilization. What is stabilization? Let me maybe define stabilization by taking a very familiar example, which is the example of an inverted pendulum. So this is a pendulum. And as you know, the pendulum has, let's say, 2 equilibrium points. This is an equilibrium point, which is stable, because when I make some perturbation of this equilibrium point, the system remains in a neighborhood of these equilibrium points. And this is, I'm cheating a bit, this is an unstable equilibrium point, because because as soon as there is a small perturbation of this equilibrium point, the system does not remain in the neighborhood of this equilibrium point. What is stabilization? You are given an equilibrium point, so here it is unstable, and you are allowed to put some control somewhere. So here the control is, let's say, horizontal motion of my hand, like that. I am allowed to make some horizontal motion of my hand. And thanks to that, I would like to stabilize the inverted pendulum around its equilibrium point. So I'm doing it, okay? But of course, we can code it. This is a robot that is in Paris that does this stabilization in a very good way, as you can see. Oops. When I was in Orsay, actually, I was teaching some stabilization. The robot was at École des Mines in Fontainebleau. And one day, each year, I was bringing my student to play with this robot and to observe that what I was teaching to them was even not enough, actually, because there is some things to do. So it was very interesting. And what I would like to now to illustrate is a use of stabilization theory in aerospace problem. And in order to introduce what I will say, I would like you to consider the so-called circular restricted three-body problem, what it is. So now we are going to the space, and there is no atmosphere. Let us consider two bodies, two massive bodies. For instance, let us consider, let's say, the Sun and the Earth, right? These are two very massive bodies. And now you consider a third body whose mass is negligible with respect to the two others. So for instance, so you consider a third body, which is a stone or a space engine or something like that. Let us say a stone. A stone has zero mass with respect to the Sun and the Earth. Now you write Newton laws, simple Newton laws. And in some rotating frame, you obtain quite simple differential equations, which are there. They are quite simple, but already very rich in terms of mathematics. Let me show you why. The very first observation that has centuries is the following. If you look at the dynamics of this three-body problem, it is very, very interesting. You can see that the dynamics has exactly 5 equilibrium points. 5, not 6, not 4, exactly 5. Look at the two massive bodies, the Sun, the Earth, and a stone. You put a stone in this system. You have a rotating frame. In this rotating frame, let me assume that the Sun and the Earth are not moving. Okay, so that I am only considering the motion of the third body, of the stone. What is known is that there are 5 equilibrium points. And indeed, you can easily imagine that somewhere in between the Sun and the Earth, there is an equilibrium point somewhere. I mean, at the point L1, you have attraction of the Sun, which is in this way, and maybe you have also attraction of the Earth, which is somewhere here. So you can guess that somewhere there is an equilibrium point, right? Right. What is maybe less intuitive is that there is this equilibrium point there, L2. But be careful, we are in a rotating frame. So at this point, at the point L2, you have to the left the attraction of the Sun and of the Earth, and to the right, you have the centrifugal force, okay, which annihilate exactly at some point L2. Same thing over there for the point L3. And same thing for the so-called equilateral points, L4 and L5. You see that here you have the attraction of the Sun, the attraction of the Earth, and the centrifugal force. Okay, so it's quite clear, actually. But it's not so easy to prove mathematically. And by the way, the 3 first Lagrange points were discovered by Euler, but Euler did not discover the points L4 and L5 that were discovered a bit later by Lagrange. And so finally, Lagrange won, And this is why they are called Lagrange points. It's like that. It's unfair, actually, but it's like that. So this is the first fact. Now a second fact is about stability of those points, which is another very interesting issue. As you could guess, the points L1, L2, L3 are unstable, exactly like my inverted pendulum, meaning that if my stone is not exactly at the point L1, but if it is just nearby, then the stone does not remain in a neighborhood of L1, but it begins to drift like that and to turn. Okay? Same thing for L2 and L3. They are unstable. While, in contrast, the points L4 and L5 are stable, meaning that if you put a stone here in a neighborhood of L5, then the stone will turn and remain around the point L5, which may seem a good news. By the way, before speaking of good news, of bad news, you have this nice four equilibrium points configuration in any three-body problem. For instance, you have the same for the Earth-Moon system, exactly the same. Or if you take the system Sun-Jupiter, you have the same. So as a very first reaction, we could think that the stability property here is a good news. Why? Because imagine that you are putting a satellite here. Then you know in advance that if you do not do anything, and this is what we would do, the satellite will remain around the point L5, and you are quiet. Okay? So it may seem a good news, but actually stability is not a good news. Let me show you why. Let us consider the Sun-Jupiter system. As I told you, there are also 5 equilibrium points. And for instance, here, you can guess that the point L4 and the point L5 are somewhere here and here. And what can you guess around the point L4 and L5? You can guess that there are many stones. It's dirty. There are plenty of stones. By the way, there are here the so-called Trojan asteroids. So many stones, some of them very big, by the way. Okay, it's normal because since these points are stable, you know, you have a kind of minimum of potential. And because of that, inside this potential, there may be many stones which remain there. So you can forget of putting some satellites here. It's not possible because the satellite will be very soon destroyed by stones. Impossible. At the contrary, now, because good news, bad news, it depends on the point of view, you know. At the contrary, the instability of the points L1 and L2 is now a good news because these are clean sites, naturally clean. Is the dream of ecology, right? These sites are not dirty. As soon as there is a stone, you know that the stone will not remain here. So let us rather use these points, L1 and L2, to observe cosmos. And indeed, these sites are already used since many years. For instance, near the point L1, since now 30 years or something like that, there is the satellite SOHO, whose mission is to observe the surface of the sun. It's only one example, because there are many, many objects around Lagrange points. Near the point L2 will be launched something like in 2 years or something like that, the next Hubble telescope, which is called the James Webb Space Telescope. It will be put there because it is a good site to observe the cosmos. Okay. And I would like to mention that, as usual, authors of science fiction had preceded scientifics by imagining that in the 60s, in a very bad series, by the way, but I like to mention it, that near the point, at the point L3, which is completely invisible to us. We cannot see what happens at the point L3. At the point L3, they had imagined that there was a planet, the planet X, whose inhabitants are nasty guys who would invade the Earth and destroy us. Okay. So you see that already in the 60s, authors of science fiction had imagined some applications of Lagrange points. A second point, which is mathematically very interesting and non-trivial, is that around each Lagrange point, there are many periodic trajectories, periodic orbits. What I claim is that thanks to mathematics, because you cannot see them, thanks to mathematics, it is known, it can be proved that around each Lagrange point, you have periodic orbits. Some of them have the shape of a circle, like that. Some others have the shape of an 8, like that. And actually, you can prove that near each Lagrange point, you can find any Lissajous orbit. This is a bit surprising. And it can only be discovered just by making mathematics. You cannot see them. And the fact, actually, halo orbits are used actually for the satellite SO, but maybe I have enough time to explain this. Let me come rather to the even more interesting point. The fact is that each of these periodic trajectories generates what is called in mathematics invariant manifolds that you can think of as being some kind of tubes, and these tubes have exactly the shape of the periodic orbit that generate them. For instance, if you take a halo orbit, which is a kind of circle, then it generates a kind of tube, which is exactly a kind of cylinder. Okay? But for instance, if you take a curve that has the shape of an 8, then it generates a tube that has the shape of an 8, like that. And these shapes, because of the Cauchy-Lipschitz theorem in mathematics, are separating, meaning that if you have a stone inside the tube, then the stone will move according to some kind of current, and it will remain in the tube. This is very remarkable. This is why I like to call these invariant tubes, I like to call them gravity currents, because these are currents due to gravity, exactly like in the sea, in oceans. In oceans, you have some currents that you can use or not. But you know that, for instance, for the Gulf Stream, if you are going to the west of Africa with a boat and you do not have any motor of your boat, so you put your boat there and you are sure that after maybe 3 or 4 months, you will be at the west of France, just by using a current which is completely for free. So what you can imagine here is that such ocean currents also exist in the space, but they are due to gravity. So we can try to use them. And we can try indeed to use them. What you can figure out is that these tubes generate some kind of tunnels of which you can make a kind of cartography. And you can move inside indeed. What you can imagine is that you have something like that. Okay? So you can use them in order to move completely for free from, for instance, from a neighborhood of the Earth to Jupiter, maybe. Except that the motion inside is very slow, of course. Like on the ocean. The motion is very slow. So maybe you can try to compute them. You can draw a kind of cartography of the solar system and try to compute all these tubes. You have also to imagine that since the planets are rotating, these tubes are moving constantly. But the calculations can completely be done. And what you have to imagine is that we have a kind of metro which is completely for free. You do not have to pay, right? The ticket is for free. But, well, it is like RER in Paris or like trains in Italy. It's very slow, right? It's for free, but it's very slow. Well, it's like that. But you can do that. You can do that, and thanks to this cartography, you can try to imagine and you can try to design interplanetary missions. Of course, this will be missions for robots, not for humans, because the time needed to go, for instance, from the Earth to Mars or to an asteroid of Jupiter is too long for a human being. But at least we can send some robots. Okay, and so I will end with, again, this picture and let you imagine that in some sense these gravity currents are a kind of free ticket maybe to, for one future to go to outside of the solar system. And I have to stop there. So thank you.
Thank you very much, Emmanuel. It was really great to have introduced us in this fascinating way and communicating the fun and all of this enthusiasm in going through this control world. So please, if there are questions, comments.
Do you have any suggestions for books or, I don't know, even articles where we can go deep inside this subject?
Yes, because I have communicated, let's say, quite much on this kind of issue, because it's a kind of issue on which you can communicate at various levels, either complete popularization or intermediate levels up to research. So my advice is that you can go to my webpage. You will see my name. You type my name and you will find my webpage, or you send me an email. And in my publications, you can find some popularization articles that on this subject that are of various levels, from the very basic popularization to articles containing mathematics and also research. So this is my advice. And then, if you would like to get some more precise, because you want to make some research in that, you can look at all these names, for instance, that I put here on this slide, just to mention that, well, we are numerous to work on these issues in Europe. There is a whole team. There are many researchers, for instance, in Spain, like Masdemont, Libre. There are many guys in France, and there are also many guys in Italy. So you will maybe recognize some names here. In particular, near Roma. Near Roma, there is a big team also working with ESA, ESA, working on that.
Other question? Okay, just, okay, you already spoke about many problems, and since we were discussing before, I think would be useful for everybody. I mean, all this new topic of deep learning, machine learning, how can the control theory can bring some insight on this, and what is his role, could be his role in this?
Well, it depends, because, you know, deep learning is rather working by similarity. So this is why deep learning is so much applied in medicine, for instance. And very likely, in few years, we will all have some softwares in our smartphones that will act more or less like a medicine guy, like a physician. I mean, you will have to do like that, and the smartphone will tell you, oh, you have a cold, so you should take this such or such drug. But deep learning here works by similarity. It's big data. It's going to read many possible data, and it works by similarities. Here, when we explore new possibilities to explore the space, we do not have, for the moment, any big data. If we had some big data, then we could use them in order to imagine some new missions. So once a system, what I say is completely general, not only in aerospace, but Once we know sufficiently a problem, may it be a mathematical problem or something else, once we know it, once we have big data on this problem, then we can work by similarity in order to compute such or such trajectory. Here, in that case, since we are exploring new issues, well, deep learning could be maybe of partial help, but this is not the main one. The main one here inside actually is geometry, this for sure. There is much geometry here inside these studies.
Thank you, Emmanuel.
Yeah.
Okay.
Hello. I would like to ask if this area has a particularly high interaction between applications and theory. I mean, even very abstract parts of the theory, like what do you do in your research is immediately applied or applicable. I mean, is there a particularly extraordinary, I would transfer, you know? Thank you, sorry for the English.
Yeah. No, it's a very good question. As I said at the very beginning, the main fact when you are doing some research is to have fun. And having fun is not necessarily related to applications. For me, it is my personal taste that in general, I choose some mathematical subjects which do have an application somewhere. In general, in another discipline, such as aerospace here, or medicine, or something like that. It's my personal taste. But you know, you may have much fun in doing, let's say, pure or fundamental mathematics that do not seem to have an a priori application. This is a matter of having fun. For instance, to mention a work that we had in common with Francesco Rossi, that guy here, we were working on sub-Riemannian geometry, on completely, let's say, unapplied issues, but we had much fun in doing that. Then what I would say too is that sometimes, if you are concerned with applications, if you are motivated by application, sometimes it's also very good to work on a, let's say, pure mathematical problem that does not seem to have application, just because it will serve to develop new knowledge that will then be useful in a more concrete problem. And this is most always the case, most always. And sometimes some mathematical discoveries take years and years to find an application. Think of the GPS, for instance, of which the very fundamentals were discovered 1 century before. So probably people who were working on fundamentals were not thinking at all of any applications. But it's like that. You make an advance in the knowledge. But let me insist on the fun. It's very important to keep motivated.
So,
Thank you, Emmanuel, but I have only a very small comment, historical comment. You had this slipping problem with the answer number 2 that was the circle, and you told us that Euler believed that the circle was the solution, right? But as far as I can remember, I think that also Galileo Galilei made the very same error, because he wrote in one book that the circle was the solution.
That's right.
And he tried to prove that.
Yeah, that's right.
Very interesting.
Right.
Thank you.
That's right. That's right. You are fully right. Galileo, famous, the famous Galileo made the same mistake. Yeah, and was trying. But you know, we can excuse them, no problem, because at that time they had not even the concept of what is the derivative. It was invented, by the way, in order more or less to solve that problem. So we can pardon them. Thank you for your comment.
okay, if there are no other questions, let's thanks warmly again, Emmanuel.